Hello. We shall be learning about torsional pendulum today. So our main derivation is going to deal with finding out the rigidity modulus using a torsional pendulum. So what is rigidity modulus? What is a torsional pendulum? So you would have learned about three different types of modulus in school: Young's modulus, rigidity modulus, and bulk modulus. So let us speak about rigidity modulus. Rigidity modulus is comes into action when there is a change in angle. You would have learned that as well. Okay, when there is a change in angle and the object tries to get back to its position. For example, you take a towel and wring it. Take a towel and twist it and leave it. The towel will get back to its position. You sit on a swing and twist and leave the swing will get back to its position. All these are examples of rigidity modulus. So then what is a torsional oscillation? What is a torsional pendulum? So I have a wire here in which is suspended a small disc, rather. So when I am twisting this disc, what happens is this wire gets twisted with respect to its axis and it is deformed. So what is happening is this disc now executes torsional oscillations in an effort to bring back the wire to its position. So this is torsion pendulum. This is what we'll use to find out the rigidity modulus of the given wire. So now let us start with torsion pendulum derivation. Start sharing my screen. So this is what we'll be learning today. Torsional pendulum. In this session, we shall learn about torsional pendulum. So what I have is, I have a wire and I have this disc which is suspended. That's what I showed you now. I am applying a couple. So you all know what a couple is. So both my fingers, one moving this way, other moving that way, and creating a motion in the same direction. So I have an applied couple, giving it a small twist. So this applied couple is given by the product of moment of inertia and angular acceleration. So moment of inertia is I and my angular acceleration is d square theta by dt square, where theta is the angular displacement as we have seen earlier. The applied couple tries to twist the wire. So what happened? This wire is opposing. It refuses to be twisted. It wants to be restored to its position, which is known as restoring couple. So you have a restoring couple which is fighting this applied couple. So this restoring couple is given by C into theta. Theta is the displacement and C is known as couple per twist, the amount of force it executes to move through one radian. So C is known as couple per twist. So we know this restoring couple is fighting against this applied couple. So at equilibrium, both should be equal to each other. So what do we write here? We write I d square theta by dt square is equal to c theta. Why? I have not written this here, but at equilibrium, these two are opposing forces, right? At equilibrium, the applied couple is equal to the restoring couple. So I d square theta by dt square is equal to c theta, or I could write d square theta by dt square, which is the acceleration, is equal to c by I into theta. So this is one expression I have. So I need to find out the time period, after which I slowly meander into finding out the rigidity modulus as well. Now these oscillations are torsional oscillations, but again, though they are torsional, these oscillations are about a mean position. You know this. They go, get back. They go, get back, which means these oscillations are simple harmonic in nature. So we have a standard equation for the time period for simple harmonic oscillations, which all of you know. So T is equal to 2 pi root of displacement by acceleration. Right? T is equal to 2 pi root of displacement by acceleration. So what we are going to do, we are going to substitute for displacement here and we are going to substitute for acceleration here. So you will have T is equal to 2 pi root of, what is displacement? Displacement we know is theta, angular displacement, theta, and acceleration. What do we have for acceleration? d square theta by dt square is c by I into theta. So what do we have? C by I into theta. So you will have this time period as equal to 2 pi root I by C. This is the time period for a torsion pendulum. Now using this equation, we are going to find out the rigidity modulus of the given wire. So to go about that, first I'll try to remove this square root. So I will have now T square is equal to 4 pi square I by C. Am I right? Oh, I'm squaring this. What is T? T is the time period taken for oscillations. That is, going and getting back is one oscillation. So T is the time period taken for one oscillation, and in this equation, I is the moment of inertia and C is the couple per twist, what we have seen earlier. So we need an expression for couple per twist, and there has been a long derivation finding out the value for this couple per twist, which is not in our purview, but the relation given is C is equal to pi n r power 4 by 2l. So here pi you know is a constant. This n or eta, this is known as the rigidity modulus of the given wire. R is the radius of this given wire. So we have a wire here. The radius of this is r in this equation. So what is L in this equation? So when you are suspending this, so this will be the point from which you are suspending. So the length from the point of suspension to this chuck. See, you see a chuck here. To this chuck is known as L, the length of the pendulum. So you have C is equal to pi n r power 4 divided by 2l. So I am going to substitute this value in the equation for T square. So I shall now have T square is equal to 4 pi square I divided by pi n r power 4 divided by 2l. So what will you have here? This 2l will go on top. You will have 2l into 4 pi square I divided by pi n r power 4. So obviously this pi is going to get cancelled. So then having this expression and rearranging, I will find an expression. I will take this here and I will bring this t square here. So here I have this n is equal to, this is 8. I have a pi here, pi I L divided by n r power 4 into t square. Now I will regroup this again. Here n is equal to 8 pi I, okay? Oh, there's no n here, sorry. This n is already gone there, sorry. This n has to go. So n, you have r power 4 into t square here, that's all. Because this n goes here, I'm sorry. So you have 8 pi I by r power 4 L by t square. I am just regrouping it. Why am I regrouping it? This 8 is a constant. Pi is a constant. Moment of inertia for this given object I is a constant. Okay. And r, the radius of this wire is a constant. But I can vary the length of the pendulum. I said it's from the point of suspension to the chuck. I can actually make the pendulum longer or shorter. So when I am suspending this pendulum, like this, right, I can suspend it from here, or I may move it and suspend it from here, which means I can vary the length. And depending on the length, the time is also going to vary. So which means L and T square are both constants here. So the rigidity modulus is given by 8 pi I by r power 4 L by T square. This is the derivation for torsion pendulum based on our syllabus. So we shall meet up next for a different discussion. Next we'll stop here.